Welcome to this explainer. Whenever you're standing on a train platform watching a high-speed locomotive hurtle past, have you ever wondered how it all works so seamlessly without just catastrophic failure? Well, today we're stepping into the fascinating world of a systems engineer to explore the meticulous, almost invisible architecture that keeps modern railways perfectly safe. We're going to break down the exact frameworks used in railway control and communications to guarantee that every single journey is a safe one.
So, how do we engineer a profoundly complex system that literally cannot fail? A railway is a massive web of interactions. You've got signaling, telecommunications, rolling stock, human drivers, and control centers all talking to each other at high speeds. To prevent chaos in an environment with absolutely zero margin for error, we can't just cross our fingers and hope for the best, right? Instead, we rely on a universally proven, highly disciplined engineering procedure. It's a structured approach that ensures every single component plays nicely together before a single piece of track is ever laid.
Here's what we're covering today. We'll start with the V-model lifecycle, then dive into defining the requirements, look at the contextual inputs, build out the system model, and finally wrap up with engineering for dependability. All right, part 1, the V-model lifecycle.
Take a look at this. The V-model is essentially our master timeline. It's got very discrete phases and hard boundaries. On that left side, we're moving downward from the initial big-picture concept, breaking it down into specific requirements and detailed design, right down to manufacturing. Then, boom, at the bottom of the V, we pivot. We start heading back up on the right side into the real world. We're installing the equipment, integrating it, and rigorously testing everything against those original requirements until we hit full operations. It's how we guarantee that what we built is exactly what we needed in the first place.
Moving on to part 2, defining the requirements.
If we zoom into the very foundation of that downward slope on the left, we hit the most critical phase of the whole thing, requirements definition. This is where we translate a messy, real-world problem into a razor-sharp engineering spec. We're deciding exactly what the system has to accomplish. Notice I said what? We aren't figuring out how to build it just yet. But if you get the what wrong here, man, the whole structure on the right side of the V is going to collapse, because you'd be flawlessly validating a totally flawed concept.
Now, these requirements generally split into 2 buckets. First up, business requirements. These come straight from the sponsors or operators, and they're usually hitting on performance or monetary goals. Like, hey, we need to run 24 trains per hour. But, engineers can't just build 24 trains per hour and go to work. So we essentially act as translators. We convert those high-level business goals into precise system requirements. This is the hardcore technical response that lays out exactly how the signaling and communications will actually make those 24 trains a reality.
Which brings us to part 3. The contextual inputs.
These requirements don't just float in a vacuum, right? They sit within a very specific environment defined by 4 critical inputs that act as our toolkit. First is domain knowledge. These are the absolute, undisputed facts we rely on. Things we know to be true, like the exact electrical characteristics of our signaling relays, or the friction values of steel wheels on steel rails. We never guess here. We build on rock-solid scientific truths.
Next up, we have assumptions. These are those tricky, unproven variables outside our immediate scope that we're basically counting on to be true. And because we don't have hard evidence for them yet, we absolutely have to track them down and verify them later on. Otherwise, we're setting ourselves up for some pretty disastrous surprises.
Third, we map out our dependencies. This is us acknowledging that, hey, we need someone else to do their job before we can do ours. For instance, if our project is delivering a fleet of high-tech trains, it's a massive dependency that another team actually upgrades the depots to handle them. If they drop the ball, our project stalls out completely.
And finally, caveats. These are the strict operational rules that kick in after the system goes live. Think mandatory maintenance standards. We can design a brilliantly safe system, but with the massive caveat that the operator actually has to perform the required inspections to keep it safe down the road.
All right, part 4, the system model.
So, once we have our contextual toolkit locked in, all those exact requirements combine to form our system model. And this splits cleanly down the middle. On one side, you've got functional needs, literally what this system physically does, like routing a train or flipping a signal to green. But equally crucial are the non-functional needs. These don't tell the system what to do, but rather how well it behaves while doing it. We're talking cybersecurity, peak performance outputs, and a very specific and absolutely vital concept called RAMs.
That leads us right into part 5, engineering for dependability.
Those non-functional needs basically revolve around this one acronym that makes or breaks the entire lifecycle: RAMS. That's reliability, availability, maintainability, and safety. These are the four non-negotiable pillars of dependability. And guys, this is huge. The cost to operate and maintain a railway over a 40-year lifespan absolutely dwarfs the initial capital cost to build it. If you don't engineer for RAMS from day one, you are looking at decades of expensive regret.
Let's break RAMS down. First is reliability. Basically, what's the probability this thing will actually work when we need it to? We engineer reliability so that when a signal tells a train to stop, we have mathematical certainty that it will. Think about it. A high-speed train can take over a mile to come to a halt. We aggressively weave out weak components because we need that mathematical guarantee that the brakes and signals are going to fire flawlessly.
Next is availability, which is all about maximizing uptime. It's the proportion of time the system is actually usable. Look, even highly reliable parts break eventually, so high availability means we build in duplicated backup systems. That way, the railway can keep processing traffic safely 24/7 without having to take the entire network offline just because of a single glitch.
Then we've got maintainability. When things inevitably wear out, how easy is it to fix them? We design these systems with modular plug-and-play parts and remote diagnostic tools. The goal is for technicians to swap things out super fast, ideally without ever having to step dangerously close to the live track, and definitely without delaying your commute.
And finally, safety, the ultimate goal: freedom from unacceptable risk of harm. We're engineering fault-tolerant systems to protect the trains, the passengers, and the staff. But if a total failure is just absolutely unavoidable, the system is hardwired to fail safe, meaning if a signal breaks, it automatically drops to a red stoplight, period. It protects everyone under all circumstances.
So, pulling it all together, from that massive macro-level V model, right down to the microscopic tracking of RAMs, this meticulous requirements definition is the invisible architecture of every safe journey. By translating big business goals into incredibly rigid technical specs, systems engineers are essentially weaving an invisible safety net that we all implicitly rely on every time we travel.
So, the next time you step onto a platform and feel the rush of an approaching train, just take a second to think about the sheer engineering marvel behind it. Think about the thousands of precise requirements and fail-safes silently grinding away in the background to guarantee you arrive safely. What unseen requirement is actively protecting you right now? Keep questioning, keep learning, and thanks for joining me on this explainer.